Hello everyone, welcome to this lecture on driving 7-segment LED displays. So in this lecture you will learn how to connect a 7-segment LED display to a microcontroller to display numbers. The material for this lecture can be found in Lab 3 handout. So you can refer to your Lab 3 handout which is available on Moodle. So before we move on, let's look at the aim for this lab. The aim is to learn how to multiplex several 7-segment LED displays. This is one of the things that we will learn. For example, if you have multiple 7-segment LED displays, how you connect or interface it to the microcontroller. Next, understand how a 7-segment LED driver program works. So we have to write code to display numbers on the 7-segment LED displays. So we will learn how to write the code for that. And then lastly, to create C programs to display numbers on 7-segment LED displays. So we will use two 7-segment LED displays and we will learn how to display numbers on that. So let's look at what 7-segment LED displays are and how you can interface them to the microcontroller. So if you look at section 2 of your lab handout, in figure 1 you can see a diagram of what a 7-segment display looks like. So the diagram on the left shows you physically how a 7-segment display looks like. So it's nothing but segments of LEDs. So it has 7 segments and the segments are labeled A, B, C, D, E, F, G and DP. So DP stands for decimal point. So it is used to display a decimal point. So if let's say if you want to display a particular number on the 7 segments, so each of these segments correspond to an LED, as you can see on the right here. So to display a number, let's say if you want to display number 7, then you need to switch on segments A, B, and C. So if you turn on the LEDs corresponding to segments A, B, and C, then the number 7 will be displayed. Now the 7-segment displays can be interfaced in either a common anode configuration or a common cathode configuration. So the diagram in figure 1 on the right shows a common cathode configuration, and the reason for that is because the cathode part of the LEDs are connected together, so they are common cathode, and the anode part of the LEDs are represented by this segment digits A, B up to DP. Now on the other hand, if you have a common anode configuration, then the anode part of all the LEDs are connected together and it is common, and the cathode part of the LEDs are connected to this segment digits A, B, C, D, E, F, G and DP. So let's say if you want to display a number on the 7-segment display, let's say if you want to display, for instance, you want to display the number 7 on the 7-segment display, then what you have to do for a common cathode configuration, you have to provide a 0 signal on the common cathode, and you have to provide a high signal on segments A, B, and C. So when you provide a high signal on segments A, B, and C, the segments A, B, and C are going to be switched on, the LEDs are going to be switched on, and you will see the number 7. Now the rest of the segments need to be low, so D, E, F, G, and DP will be low. So those LEDs will be switched on. So this is for a common cathode. Now if you have a common anode display, as shown in this, and if you want to display the number 7 on the 7-segment display, so I, B, and C, these need to be low, logic low, and the rest D, E, F, G, and DP will need to be high. Now the common anode the common part is supposed to be high. So when this is high, so this will be 5 volts. So current will flow in this direction through the LED, and then since segments A, B, and C are low or 0 volts, then these LEDs are going to be switched on. So this is for a common anode display. In this lab, we are only going to be using a common cathode display. So let's see how we can interface a common cathode 7-segment display to a microcontroller, and how the driver program for a common cathode 7-segment display will work. So as I've explained earlier, a common cathode is where the cathode part of the LED is common and the anode part of the LEDs are separate, and they are labeled by the segments A, B, C, D, E, F, G, D, P. So if you want to display a particular number on a common cathode 7-segment display, let's say if you want to display number 7, you need to switch on A, B, and C. So in this case, segments A, B, and C will be high, and D, E, F, and G will be low. And of course, the common will be low as well. Now, if you want to display a particular number, we start from number 0, and let's say all these segments are interfaced to a particular port. So let's say segments A, B, C, D. The anode part of segments A, B, C, D up to decimal point is connected to port C pins 0, 1, 2, 3 up to 7. So A is connected to C0, B is connected to C1, C is connected to C2, D is connected to C3, and so on. So if you want to display number 0, let's say, then which segments need to be high? Segment A, B, C, D, E, and F. So segments A, B, C, D, E, and F will be high, and the rest of the segments will be 0. So let's say in this case we have decimal point as well, which will always be 0. So we are not considering decimal point here. Now, if you want to display the number 0, then the common part of the common cathode display needs to be 0 or low, and then you need to send this combination of bits to display number 0. So this combination of bits in hexadecimal is 3F. So this is 3F hex, and this will be written to port C because my common cathode segments are connected to port C pins. So if I send this data 3F to port C, it's going to display 0. Now if I want to display 1, then my segment A will be 0, B will be high, C will be high, D will be 0, E will be 0, F will be 0, G will be 0, and DP will be 0. So if I want to display number 1, only B and C needs to be high. So this combination of bits again in hexadecimal, this comes to 0, 6 hex. So if I write 0, 6 to port C, then it's going to display 1 on the 7 segment. Now we can do the same thing for the rest of the numbers. If you want to display number 2, the segments that are going to be switched on are A, B, G, E, and D. So if you want to display number 2, A will be high, B will be high, C will not be high, D will be high, E will be high, F will not be high, G will be high, and decimal point will be low. So now if I want to display number 2, then what I have is the hexadecimal digit 5B. So if I put the data 5B in port C, then it's going to display number 2, assuming the common cathode 7 segment is connected, and it's connected in this way to pins 0, 1, 2, 3 up to 7, where A is connected to 0, B is connected to 1, C is connected to 2, D is connected to 3, and so on. So we can do this for the rest of the numbers, and you can see 3F, 06, 5B. So these are the hexadecimal code for the first 3 digits. Now if you look at your lab handout, if you go on to the source code part, you can see that the first 3 hexadecimal digits on line number 6 are 3F, 06, and 5B. So this is for the numbers 0, 1, 2. And the rest of them are also given for 3, 4, 5, 6, 7, 8, and 9. So we can only display numbers 0 to 9. We can also display some characters like some alphabets, but we'll look at that later. So that's why in your code you have an array declared with these hexadecimal digits. So this is essentially your 7-segment driver. So when you output these values on a particular port, and if your 7-segment is connected to that port, then these values are going to give you these values are going to display those decimal numbers up to from 0 to 9 on the 7-segment display. Now, as you have seen previously, if you want to interface a single 7-segment display to the microcontroller, you need to have at least 7 pins on the microcontroller. So if you want to connect, let's say, multiple 7-segment displays, let's say if you want to connect 3, then you need to have 21 pins. But many microcontrollers may not have that many pins available, or in your project you may not have that many pins available to interface several 7-segment displays. So what we are going to do is we are going to learn how we can multiplex multiple 7-segment displays together and connect them using less number of pins. So in this case, if you look at figure 2 of your lab handout, then you will see 2 7-segment displays are used here, and they are multiplexed 7-segment displays. So what it means is that if it is a common cathode display, then all the segments A, B, C, D, E, F, G, and DP, they are connected together for both of the displays. So display 1 and display 2, the segment pins are connected together, and then they are interfaced to the microcontroller. So in this case, they are connected to port B of the microcontroller. Now the common part, so this is the common part. The common parts of both the displays are not connected together. So for display 1, the common part is this one, and for display 2, the common part is separate. So they are connected separately. So what happens in a multiplexed display is that first you're going to display a number on segment 1, and then you're going to display a number on segment 2. So what will happen is you will activate segment 1. So if I make segment 1 low, that means I'm activating display 1. So if segment 1 is not low, if it is high, then it's deactivated. So if it is low, then it is activated. Likewise, segment 2, if I make it low, I am activating, and if I make it high, I am deactivating. So what will happen is you will activate one of the segments, and then you will display a number. So you will send a combination of hexadecimal digit to display an appropriate number, and then you will deactivate that segment and activate the second segment, and then you will send another combination of number, or the number that you want to display on the second segment. Now you're going to do this repeatedly for a number of times, and you're going to do this so fast that the microcontroller that you are going to see on an average both the numbers displayed at the same time. So this is how multiplexing works. Since we have connected all the segments together, it is expected that if I display a number on segment 1, the same will be displayed on segment 2. But this is not the case, because I am activating segment 1, displaying the number there, and then I'm activating segment 2 and displaying another number there. And then I'm doing this repeatedly for a number of times. So if I want to display 1, 2, so let's say if I want to display 1 and 2, then I'll activate display 1 and send in the combination of bits that need to activate these two segments. Then I'm going to deactivate segment 1, activate segment 2, and send the combination of bits that are going to switch on those segments that display number 2. So by doing this quickly, what your eyes are going to see is the number 1 and 2 displayed together. So your eyes are not going to notice the difference. So the number 1 and number 2 are going to be displayed together according to your eye. And that's a phenomenon commonly known as persistence of vision. Moving on to the source code, you can see that the first 3 lines are our generic hash lines. So these are preprocessor directives. Hash include hash fuses and hash use. Line number 6, I have explained that. So to display number 0, I need to send a hexadecimal digit 3F to the port to display number 1, 0, 6, to display number 2, 5B. So this is for a common cathode display connected to my microcontroller. So whichever port this is connected to, if I send this data, then this is going to display those respective numbers up to number 9. Now from line 8, you have a function called void display number. So what this function does is, if you have a number as an integer passed into this function, it will try to display that number. So for example, if you want to display the number 25 on the 2 7 segment displays as were connected in the previous step, if you want to display the number 25, so these are the segments that are going to be switched on. Now what happens here is the number 25 is being passed into this function as n. So this function output b is going to output a hexadecimal digit from this LED map array. So what is it going to output first? It's going to output n over 10. So if you divide, let's say if n is 25, and if you divide 25 by 10, what you will get is not 2.5, what you'll get is just 2, because this is integer division. So you'll get only 2. So this will display first number 2. So if it is 2, and if 2 is passed here into this array, it's going to output 5B on port B, and 5B is going to display 2. Now these two LEDs, so D5, this is going to activate display 1 on, and D7, this is going to switch off display number 2. Now after a few millisecond delay, then it should display the number 5, isn't it? So what happens is you pass in to this array n modulus 10. So n modulus 10 is basically, it will give you, so modulus is going to give you the reminder. So if you divide 25 by 10, you'll have 2 reminder reminder 5, isn't it? So mod is just going to give you the reminder. So n modulo 10, if n is 25, is going to give you 5. So LED map, and you are passing in 5, so it's going to pick out this value and pass it to the port. So the port is going to display, or it's going to switch on a combination of bits based on this value 60, and that will light up the corresponding segments to display number 5. And again, if you look at pins D5 and D7, D7 is now low, so segment 2 is now activated, and D5 is now high, so segment 1 is deactivated. And then there's another delay of 45 milliseconds. Now if we move down to the main program, so this is what the main program does. So void main, so it does not return. So an integer I is declared, an integer count is declared as 0. So I is basically a loop counter, so for the for loop, and count is basically what we want to be displayed on our 7-segment display. So there's a while true loop, that means this loop is going to loop until as long as you supply power to the microcontroller. Now you have a for loop here which loops 10 times, since I is less than equal to 0, from 0 to less than equal to 0. So this is going to loop 11 times. So it's going to display a number. So is going to display the number that is count. So initially count, the value of count is 0. So it's going to display 0, 0 on the 7-segment display. And then there's an if else statement there. So if count is equal to 95, then it's 0. But count is 0, so it's not 99. Else count is equal to count plus 1. So it's going to go in the else part, and it's going to keep on incrementing count. So this part is going to loop 11 times and display the same number, which is initially 0. And then this checks if this number is 99. So what you should see is when you run the program, your 7-segment display should start from 0, 0, 0, 1, because every time it's going to increment. Count is going to increment until it reaches 99. So when it reaches 99 or 99, it becomes 0. So after it reaches 99, it's going to become 0, and then count again 1, 2, 3 up to 99. So that is what you should see. Now this number, why is it looping 11 times? If you increase this the number of times that you want to make this loop, then this every number or every count value is going to be displayed for some amount of time. So if you increase this from 10 to 20, then it's going to be displayed for more amount of time. So that is what this loop basically controls, because it's repeatedly displaying the same thing. So which means it's going to do the same thing but in a loop. So if you increase the loop count, it's going to do the same thing, display the same value, but for a longer period of time. So that's what this program is going to achieve. Now there are some notes given in section 5. So it says this example does not use decimal points. So we are not using the DP part of the 7-segment display. Unlike the onboard LEDs, there is no built-in current limiting resistor on the 7-segment display units. Many applications will require a series resistor on each of the segments. In this case, we use 470 ohm resistors to ensure the LED segments are not damaged. Next, it says, unlike the previous programs, this program writes all I/O pins on one port at the same time using output _B. So basically what this means is that if you have port B, so every port is an 8-bit port except a few ports. So port B is a 8-bit port, which means pins B0, B1, B2, B3, B4, B5, B6 and B7. So you can use one single function called output _B, and you can write a value using a single function. So if you want to write, let's say, a combination of bits in this 0 1 1 1 1 0 1 0. So let's say you want to write this combination of bits, then you need to do output _B, and in brackets you need to pass in a hexadecimal value. So you can pass in a hex value here. So for this combination of bits, if you want, let's say, B0 to be high, B1 to be high, B2 to be high, B3 to be low, B4 to be low, B5 to be high, B6 to be low, and B7 to be high. So this comes to 1010 is A, and 0111 is 7. So this comes to A7 in hex. So what you can do is use this function and write 0xA7. So this is going to make all those pins high in port B. So it is going to make those combination of pins in port B high. So that's the importance of this function. Next, it says the LED map array specifies for each number which segments need to be on or switched on. The first entry, which is 0, needs segment A, B, C, D, E, F, and so on. Sorry, A, B, C, D, E, F to be on. So this is B0 to B5, or in hex 3F. So I have explained this clearly, how you can display, if you have a common cathode display, how you can display 0, 1. So you need to have a combination of bits specified in hex to be able to display number 0, number 1, number 2, and so on the 7-segment displays. Now, if you look at section C exercise, so this is what you have to do on your own. You have to make a version of the program above that counts from 00 to FF. So in hex. So it must count from 00 up to 09, and then 0A, 0B, up to 0F, and then after 0F it should be 10, 11, and then 1A up to 1F, and then it should change to 20, and so on, and then up to FF. So you have to modify the program to be able to display all this. So the 7-segment display can display digits A, B, C, D, E, and F. So you have to modify the program to be able to achieve this objective. So once you are able to do, I'll create a submission link on Moodle where you can submit the code for this exercise. Thank you.